Okay, students, so far we have seen two applications of integral calculus, namely the application of integral calculus to find the area and the application of integral calculus to find volume of revolution. Now, in this presentation, we'll try to see other applications of integral calculus, namely the application of integral calculus to solve problems related to work done by a force, and problems related to motion of a particle. Now, at the end of this topic, you are expected to find work done by a force on an object, and you are expected to find displacement, velocity, and acceleration of a moving body that moves in a straight path. Now, the first one is work done. As you know, in your physics, work done is nothing but the area determined by force displacement, force versus displacement graph. In force versus displacement graph, area always represents work done. And as we know, area is nothing but integral from a to b of f of x dx. Therefore, work done can be defined as the integral from a to b of f of x dx. Now, for instance, let us have the following example. Find the work done when a particle is moved through a displacement of 10 meters along a smooth horizontal surface by a force F whose magnitude is 6 Newton. The force is a constant force, a fixed force. Therefore, area is nothing but, this is rectangle, area is base times height. Therefore, the work done will be base is 10, and height is 6, 10 times 6, it is 60 joule. Now, let us see the integral approach to work done. Work done is integral from a to b of f of x dx. Now, in our case, from a to b is from 0 to 10. My function f of x is simply 6 Newton, 6 dx. So I'll have the integral is 6x, evaluate this from 0 to 10. So I'll have 6, 10 minus 0, that is 6 times 10, 60 joule. Therefore, the work done will be 60 joule. Or simply base times height, because it is rectangle. Now, when the force is 9 minus half x, of course this is what? A trapezium. And we know that the area of a trapezium is half times base 1 plus base 2 times height. So, work done using ordinary formula is, it is area, but the area is, because it is a trapezium, half b1 plus b2 times height. Half times, what is base 1 and base 2? The two parallel sides. This is 9 Newton. And when x is 10, what is the height? Half of 10, 5, 9 minus 5, it is 4. So therefore, the two bases are 9 and 4. 9 and 4. 9 and 4. And the height is nothing but the distance between the two parallel sides, that is 10. So, half of 10 is 5. 9 plus 4 is 13. 13 times 5, that is 65. Now, let us apply the integral approach. Work done is the integral from a to b of f of x dx. Now, from a to b, in our case, from 0 to 10. And my function is 9 minus half x, okay, dx. Now, what is the integral? It is 9x minus the integral of this one, 1 over 4 x squared. Let's evaluate this from 0 to 10. So, 9 times 10 minus 0, minus 1 over 4, 10 square minus 0 square. 9 times 10 minus 1 over 4, 100 minus 0, it is 100. So 90 minus 1/4 of 100 is 25. 90 minus 25, 65 joule. The same result. Okay? The same result. So the work done will be 65 joule. Now, when f is 100 minus x squared, I think this is not a simple region, therefore we have to go through the integral approach. So work done is the integral from a to b of f of x dx, from a to b, in our case, from 0 to 10, of my function is 100 minus x squared, 100 minus x squared dx. So the integral will be 100x minus 1/3 of x cubed, evaluated from 0 to 10, 100, 10 minus 0, minus 1/3, 10 cube minus 0 cube. So you'll have 100 times 10 minus 1/3 of, this is 1000, 1000 minus 0, 1000. So 100 times 10, 1000 minus 1000 over 3, 3000 minus 1000, 2000 over 3. So if you like dividing 2000 by 3, we'll have 666.7 joule. So this is the work done by this variable force. Now let us see the application of integral calculus in order to solve what we call motion problems. As you know, for rectilinear motion, acceleration is constant. It is what? Constant. So if you have given a constant acceleration, obviously velocity at any time t is given by the formula, the integral of the acceleration function. But acceleration is constant, it is a times dt. The integral of this constant is at plus some constant. That constant is the velocity at t equals 0, therefore we can call this v0. So the velocity at any time t for rectilinear motion will be, for uniformly accelerated motion will be at plus v0, or v0 plus at. And displacement is nothing but the integral of the velocity function. Velocity is at plus v0 dt. Now the integral of this will be half of at squared minus v0 t plus some constant. That constant is the displacement at t equals 0 second. We usually take it at 0, or we can simply say it as S0. So displacement at any time t can be found by this formula. Half at squared plus v0 t plus S0. Now let us see practical applications. Example 1 says, assume that a particle moves along a straight path with a constant acceleration 8 at t equals 3 seconds. The displacement and velocity of the particle are 57 meter and 31 meter per second. Find the velocity and the displacement at t equals 10 seconds. Okay. Now in this problem we have given a constant acceleration that is 8 meter per second square. So acceleration is constant, it is not time dependent, and that is equal to 8 meter per second square. And the question is to find displacement and velocity at time t equals 10 seconds, given that displacement and velocity at time t equals 3 seconds are 57 meter and 31 meter per second. So we have given velocity at t equals 3 seconds is given to be 31 meter per second, and displacement at t equals 3 seconds is given to be 57 meter. And the question is to find velocity at t equals 10 seconds and velocity, displacement at t equals 10 seconds. Now, first let us try to find the following for velocity. Velocity is nothing but the integral of the acceleration function, okay? But the acceleration is a constant. It is given to be 8 meters per second square, so 8 dt. That means the integral will be 8t plus some constant. That constant is the initial velocity of that moving object. Now, we have given that v of 3 is 31. V of 3 is 31. Now from this we can calculate for v naught. So v of 3, 31 means 8 times 3 plus v naught is 31. 24 plus v naught is 31. Therefore, the initial velocity is 7 meter per second. This is the initial velocity of that moving object. So, we can write the velocity of this particle as velocity is, it is given by the formula 8t plus v naught. It is 8t plus v naught. But my v naught is calculated to be 7, so I'll have 8t plus 7. This is the velocity at any time t. And what we are asked is to calculate the velocity at t equals 10 seconds. So it is a matter of substituting 10 in place of t here. So velocity at t equals 10 seconds will be 8 times 10 plus 7, that is 87 meter per second. Therefore, at time t equals 10 seconds, the velocity of that moving object will be 87 meter per second. And the second question is to calculate displacement at t equals 10 seconds. First, let us try to find the displacement function. The displacement function is nothing but the integral of the velocity function. But the velocity function is 8t plus 7, so dt. The integral is 40 square plus 70 plus some constant. That constant is the displacement at t equals 0 second, and we can call it simply S naught. Therefore, S of 3, this is given to be, S of 3 is given to be what? 57. So if S of 3 is 4 times 3 square plus 7 times 3 plus S naught is given to be 57. This is 9 times 4, 36 plus 21 plus S naught equals 57. 57 plus S naught is 57. From this, S naught is 0. So let's rewrite the formula for S of t. S of t is 40 square plus 70 plus S naught, but S naught is what? It is 0. So the question is to calculate displacement at t equals 10 seconds. So it is a matter of substituting 10 in place of t. So you'll have 4 times 100, 400 plus 70, that is 470. This is the displacement of the particle at t equals 10 seconds. Now let us see the answers. The first one is 87 meter per second. The second one is 470 meter. Now let's pass to the second example. A particle starts from point P with a velocity of 5 meter per second. Here we have given initial velocity is given to be 5 meter per second. if it is moving along a straight line with an acceleration it is not a constant, it is time dependent, it is given by 3t square. At time t second, find the acceleration, velocity and displacement at t equals 5 seconds. The question is, find the acceleration at t equals 5 seconds, find the velocity at t equals 5 seconds, and find the displacement at t equals 5 seconds. These are the questions. Now from the acceleration, first the acceleration is given to be 3t square. Therefore, the acceleration at t equals 5 seconds will be 5 square, 25 times 3, that is 75. Therefore, the acceleration at t equals 5 seconds will be 75. This is the first answer. Now to find velocity at 5 seconds, first let us try to find velocity at any time t. This is the integral of the acceleration function. Okay? Now acceleration is 3t square dt, and the integral is t cube plus some constant v naught. But v naught is given to be 5, so you'll have plus 5. Therefore, the velocity at t equals 5 seconds will be 5 cube plus 5, 125 plus 5, that is 130 meter per second. Now at last, let's find the displacement. Displacement is the integral of the velocity function. The integral of the velocity function is t cube plus 5 dt, and the integral is 1 over 4 t cube, t power 4 plus 5t plus some constant. We can assume the displacement at t equals 0 as simply 0. So plus 0. So displacement at t equals 5 will be 1 over 4 times t the power of 4. 5 is the power of 4 plus 5 times 5. This is 625 over 4 plus 25. 4 times 25, 100, 725 over 4, and that is 108.25. Is that 108? 725 divided by 4, 1 times 4, 32, 8, 32, 5, 1, yeah, 181.25. So let us see our answers. 75, acceleration is 75, velocity is 130, and displacement is 181.25. Okay, students, so far we have seen about 4 applications of integral calculus. One is area, the other one is volume, the third one is work done, and the fourth one is about motion problems. Now in this presentation we'll try to see additional 2 applications of integral calculus, namely the mean value theorem and the fundamental theorem of calculus 1. And as the end of this topic, you are expected to state and apply mean value theorem, and you are expected to state and apply the fundamental theorem of calculus 1. First, let us try to see what mean value theorem for integrals say. It says, suppose we have given a function f that is continuous on a closed interval a comma b. As far as this function is continuous on this closed interval, it says there must exist a number c between a and b such that f of c equals 1 over b minus a times the integral from a to b of f of x dx. And this value f of c is known by the name mean or average value of f on AB. Now let us see the application of the mean value theorem. It says we have given f of x equals x squared on the closed interval 0, 2. The first question says, find the average value of this function on the closed interval 0, 2. According to mean value theorem for integral, average value of a function f over the closed interval a, b is given by the formula 1 over b minus a, the integral from a to b of f of t dt or f of x dx. Now, my function f of x is given to be x squared and the interval is 0, 2. Therefore, the average value of f on this closed interval will be b minus a to minus 0. The integral from 0 to 2 of f of x is x squared dx. And that is 1 over 2. Integral from 0 to 2 of x squared. The integral of x squared is obviously 1 over 3 x cubed. Evaluate this from 0 to 2. So you'll have 1 over 6, 2 cubed minus 0 cubed. 2 cubed is 8. So times 8. That is by 2, 4, by 2, 3. So the average value of this function over the closed interval 0, 2 will be 4 over 3. And the second part of this question says, verify the existence of the number c in the interval 0, 2 such that f of c equals the average value. Now, find the number c whose existence is guaranteed by the mean value theorem for integral such that f of c equals the average value. What is f of c? F of x is x squared, therefore f of c will be c squared equals average value, that is 4 over 3. 4 over 3. Now taking the square root of both sides, we'll have c equals plus or minus of the integral of 4 over 3 plus or minus of 2 over square root 3. Rationalizing the denominator, we'll have plus or minus of 2 root 3 over 3. Now, which number is found in the interval 0, 2? I think it is plus 2 root 3 over 3. Therefore, the number c, whose existence is guaranteed by the mean value theorem for integrals on the interval 0, 2 will be 2 root 3 over 3. The second example says, let f of x equals 4x minus 7. Let us see the answer for this one. Yes, the answer for A is 4 over 3, and the answer for B is 2 square root 3 over 3. Now question number 2, we have given a function, find the average value of this function on the closed interval 3, 5. Average value, average f average, is 1 over b minus a. The integral from a to b of f of x dx. Now, a and b, the interval 3 to 5. So, 5 minus 3, b minus a. The integral from a to b, f of x is 4x minus 7. 4x minus 7 dx. So, 1 over 2. The integral of 4x is to x squared minus 7x. Evaluate this from 3 to 5. Half of 2, it is simply x squared minus 7 over 2 x. Evaluate this from 3 to 5. That is 5 squared minus 3 squared minus 7 over 2. 5 minus 3. 25 minus 9 is 16 minus 7 over 2 times. This is 2. 2 cancelled is 2. 16 minus 7, that is 9. Therefore, the average value of f of x on the interval 3, 5 will be 9. So the answer for this question will be 9. Okay, let us see the other application of integral calculus. It is known by the name fundamental theorem of calculus 1. It says Suppose f is a continuous function that is continuous on an interval I containing more than 1 point, and let a be any number in this interval. Assume that a function f, capital F, is defined this way. Capital F of x is the integral from a to x of small f of t dt. These two are two different functions. This the integrand is small f, and this one is capital F. For every x in I, then capital F is differentiable. If capital F is defined in this way, then you will find capital F to be a differentiable function, and its derivative is equal to the integrand function that is a small f of x. Now let us see the application of this one. Here we have given capital F of x. It is defined as the integral from 1 to x of ln t dt for x greater than 0. The question is find the derivative of this function. Now, capital F of x is nothing but the integral from 1 to x of ln t dt. The question is find f prime at x. F prime at x, it is a matter of writing the inner function in terms of x. So you'll have simply ln x. So the integral of this function is ln x. If it were, for example, to the power of t, we'll have what? To the power of x. If it is cos t, we'll have cos x. Therefore, it is a matter of changing the variable from t to x. So you'll have ln x. So f prime at x is ln x. The second one, find the derivative of this function, the integral from x to 2 of t square e power t dt. The question is find the derivative with respect to x of the integral from x to 2 of t square e power t dt. As you remember, the fundamental theorem of calculus 1 says if capital F of x is written in the form a from a to x of f of t dt. Here the lower limit of integration is constant, the upper is a variable. If that is so, f prime at x is a small f of x. Now in this case, the lower limit of integration is not a constant, rather it is a variable, but the upper limit of integration is a variable, it is a constant, it has to be a variable. So we can change this as the integral from x to 2 can be written as the negative of the integral from 2 to x of t square e power t dt. Now let's take the negative out, the negative of the derivative with respect to 2 of the integral from 2 to x of t square e power t dt. And obviously we can apply here the fundamental theorem of calculus 1, and the derivative will be, it is a matter of replacing t by x. So you have x square e power x times negative 1, or simply minus x square e power x. This is the derivative. So the derivative is minus x square e power x. The last one, we have given a function capital F in this way. Capital F of x is the integral from 2 to x, from 2x to 7x e power t cos t, e power t cos t dt. Now we can write this as the integral from 2x to a certain constant k e power t cos t dt plus from that constant k to 7x e power t cos t dt. Now since the constant must be in the lower limit of integration, we can write this as the integral from k to 2x of e power t cos t dt plus this is the integral from k to 7x e power t cos t dt. Now, what is the derivative of f of x? The derivative of f of x is the derivative of this one. It is a matter of replacing t by 2x. So I'll have e power 2x cosine of t. T is what? 2x times, it is composition. What is the derivative of 2x? It is 2. Plus, let's substitute 7x in place of t here. So I'll have e power 7x cosine of 7x times the derivative of 7x, that is 7. So I'll have minus 2 e power 2x cos 2x plus 7 times e power 7x cos 7x. This is the derivative of f at x. But what we are asked is to find the derivative at 0. So we'll have the derivative of f at 0 will be negative 2 e to the power of 0 cos 0 plus 7 e power 0, this is 0, cosine 0. Obviously, this is 1, so you'll have negative 2, this is 1, times 7 is 7, and the sum will be 5. Therefore, the derivative of f at 0 will be 5. So by this, we have come to the end of applications of integral calculus. So far, we have seen about 5 or 6 different applications of integral calculus.